We have two rather different topics to work through to complete our discussion of gases. Both of these are going to be relatively short pieces, so I've combined them into one video, which will deal with first partial pressures and then with a little bit about real gases and how we might treat things that are not well described by the ideal gas model. First, we'll take up the idea of partial pressure. Partial pressure is often an interesting and useful concept when we talk about a mixture of gases, okay? The simplest way to describe this is the partial pressure of a particular gas is what would the pressure be if only that gas were there in the container and if whatever other gases are in the mixture were just somehow removed or taken away, okay? A good example of that is just air. And so if I take the air in the room where you are, and for purposes of argument, let's just say it's 80% nitrogen and 20% oxygen. That's about right. We could get better numbers and include trace amounts of other things. But those would be the percentages, let's say by moles, because that's about the right numbers for that. Right, so that says of all the molecules in the room that you're sitting in while you watch this, about 80% of them are nitrogen, 20% of them are oxygen, okay? Let's suppose the pressure is at 1 atmosphere. Right, if the pressure is at 1 atmosphere altogether, then suppose only the nitrogen were there. Well, if you think about the gas law, it says P is equal to nRT over V. Right. If I took away all the oxygen, which would be bad, I suppose, from a breathing standpoint, but if all the oxygen were suddenly removed, I'd have 80% as many molecules, right? That means I'd have only 80% as many moles, and that means my pressure, what I could then call the partial pressure of nitrogen, would be equal to 0.8 atmospheres. And similarly, the pressure of oxygen would be equal to 0.2 atmospheres under those conditions, right? There's a way to make this into a generalizable expression. It says that the partial pressure of a gas, call it I, where I is just one of the gases in a mixture, is equal to what we can call X sub I times the total pressure. And this X sub I here, that's what we would call the mole fraction. Right. That's the same idea as I just used down here, right? When I just said, well, if 80% of the molecules are nitrogen, if I keep 80%, throw away 20%, I'm going to throw away 20% of the pressure, right? Because the gas law here says it doesn't matter whether it's moles of nitrogen or moles of oxygen, they both contribute the same to the pressure, right? This is just a fancier way of writing that or saying that. It says, in that case, I could say the mole fraction of nitrogen is 0.8 and the mole fraction of oxygen is 0.2. That's literally all there is to that equation up there, okay? This is, again, a useful idea sometimes if we're dealing with gases that are mixed together. In practice, there are certain ways to measure gases that would only measure the pressure or the number of molecules, say, of one gas. That would just give us a direct reading of the partial pressure of that gas, right? If you're worried about, say, trace levels of carbon monoxide in a house or something like that, what you care about is what is the partial pressure of carbon monoxide molecules, because that's going to tell you how many of those are present without regard to what else is present in the air. That would be a situation where the partial pressure would be a handy idea. I'm going to do a calculation here just to illustrate this idea, okay? And this is a situation where the partial pressure would probably be a relatively simple way to handle things. So I've got here a series of bulbs. One of them contains helium, one neon, one argon. They're just drawn in bright colors there to make them easy to see. That is not meant to imply in any way that helium is yellow or neon is red or anything like that, because that's certainly not the case. Right. They have different volumes. I've got a couple of 1 liters and a 2 liter, and I've got different pressures in all of them as listed there. And it says they're all at the same temperature, all at 0 degrees C. All of those things would definitely be gases at that temperature. They'd be well above their boiling point, so we could reasonably expect them to act like ideal gases, right? So maybe I have that whole thing sitting in an ice bath or something. I've got originally each gas is in its own bulb. I've got valves you can see there sitting above them. So the idea is I take those valves, I open them up, I let the gases mix. Okay, in order to make my calculation simple, I'm going to assume that the tubes that connect the bulbs have zero volume. Another way of saying that is that the total volume of that tubing would be negligibly small compared to the eventual 4-liter volume that I'll have when all those bulbs are connected together, right? So once I open all 3 valves, then the gases are not going to stay in their individual containers, right? When I open the valve on the top of the argon bulb there, the argon is readily going to start finding its way out into the tube, and it's going to wander around and eventually find its way into the other bulbs. Similarly, the helium and neon are going to diffuse out. They're going to move out into their own exploration of space. And eventually, I'm going to have a situation where all 3 gases are evenly mixed throughout all 3 bulbs. Okay. The question says, when I have the same mixture in each bulb, it might take a while, depending if the tubing's really small, take a while for that to happen, but it'll get there eventually. That's what we mean by saying let it equilibrate, right? I want to find the partial pressure of each gas and the total pressure when I get to the end, okay? So I'm going to start off with the helium. The way I'm going to do this is I'm going to treat each gas as going from its original pressure and volume, and I'm going to just expand its volume from its whatever the value was up to 4 liters, right? Because when I have all 3 bulbs connected, then my total volume is going to be 1 liter plus 1 liter plus 2 liters, so that gives me 4 liters of total volume. Right. So let's just see what would happen to the pressures when we do that. I'm going to start with the helium. The helium was initially, I'm going to say pressure and volume are what's changing, right? R and T are all fixed. Because if I go back for a second, I'm not adding or subtracting any gas, right? All I'm doing is letting the number of moles that are there move around and be in a different space. So if I wanted to set up an equation before I go to the next slide, I'll do this. I'll say PV equals nRT. That's my starting point always, right? I'll say that for each individual gas, N is fixed, R is always fixed, and T is fixed. So that says when I change the volume, I can say PV is constant, right? And that means I can say something like initial pressure times volume is equal to final pressure times final volume. That's what I'm going to use to solve the problem. For my helium, my initial pressure was equal to 1/2 atmosphere. My initial volume was equal to 1 liter. And my final volume is going to be equal to 4 liters, because that's going to be true for all of them, right? So my equation, I said that PIVI was equal to PFVF, and I could have just used 1s and 2s. It doesn't really matter what I use for the labels. But that means my final pressure, which is going to be my partial pressure of the helium, is equal to the initial amounts, PIVI, over the final volume, PF. So that says I'm going to get 0.5 atmospheres for the initial pressure, times the initial volume of 1 liter, final volume of 4 liters, and it's pretty obvious that says I divided the pressure by 4, right? So I'm going to get 0.125 over here for my partial pressure of helium. So this is what I might label that way, the helium at the end, okay? Suppose I wanted to do the neon. Okay, I need to flip back because I don't have what the numbers were. For the neon, I had originally 1 liter and 0.4 atmospheres. So I'd get PF equals 0.4 atmospheres times 1 liter divided by 4 liters. And that obviously gives me 0.1 atmosphere. So that's equal to the pressure of neon. And I had argon in the last one, and I think the argon started off being 0.2 atmospheres in 2 liters. So do the same calculation. 0.2 atmospheres in 2 liters, it goes to 4 liters. So now it's got 0.1 atmosphere for its pressure. So that's P argon. If I wanted the total pressure, The easiest way to get the total pressure, because those calculations were all easy to do, right, is just to say the total pressure is the sum of all the partial pressures, because those are the only gases in there. So it's the helium plus the neon plus the argon. I put all those in and I add up those numbers, and that says my total pressure must be 0.325 atmospheres. Okay. That's actually a simpler way to find the final total pressure, probably, than anything that tries to do it by some other means, right? I had the temperature, so I could have actually found the numbers of moles of everything and added those together and done that. This is at least as easy to do as that, and all it requires is that I have this general sense of being able to do the partial pressure to get things put together, okay? And that's exactly what we did there.